Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study an important result about maximal ideal, or which is necessary and sufficient condition for an ideal to be maximal in terms of its quotient ring. So the result written brief is M is maximal ideal if and only if R by M is a field, and the detailed statement of the theorem is written here. If R is a commutative ring, the ring must be commutative ring with unit element, and M is an ideal of R, then M is maximal ideal of R if and only if R modulo M or R by M is a field. So that means M is maximal ideal of a commutative ring with unit element if and only if its quotient ring R by M is a field. And thus the statement is necessary and sufficient. Statement is about necessary and sufficient condition, and there will be two parts we shall prove. That means if M is maximal ideal of R, then R by M is field, and conversely if R by M is a field, then M is maximal ideal. We have earlier studied what is maximal ideal, and also we have studied the quotient ring R modulo M or R by M. So what is the definition of maximal ideal? If M is an ideal M of a ring R is said to be maximal if there is another ideal U, and such that M is contained in U is contained in R, where M is not equal to R, then this implies either U is equal to M or U is equal to R. Then M becomes maximal ideal. That means actually there is no ideal between M and R. And if it is such, then this U must be equal to M or this U must be equal to R. And that's why it is called maximal ideal. This we have studied in our earlier lectures. And also we have studied what is the quotient ring. R, if M is ideal, then the quotient ring R modulo M or R by M is having the elements of the cosets R plus M, where R belongs to R. These are the elements of R by M, and we have also studied this is itself is a ring. And if the condition is regarding maximal ideal, M is maximal ideal, then R by M is field, and vice versa. This we have to prove. Now we shall start the proof. Here it is given M is ideal of ring R. M is ideal of ring R. So it is an ideal, and therefore the quotient ring is defined like this. R by M is, or R modulo M is, the quotient ring having the elements of this form, cosets R plus M, such that R belongs to R. Now here R is commutating ring with unit element, and therefore R by M is also a commutative ring with unit element, that we shall get. Since R is a commutative ring, so this is a subset of R, and therefore commutative ring with unit element. R by M, its quotient ring R by M is also a commutative ring. With unit element. Now you see, if one is unit element of R, then what will be unit element of R by M? It is of this form. So it will be 1 plus M. If 1 is the unit element of R, then 1 plus M will be unit element of R by M. Similarly, 0 is the additive identity for R. Then 0 plus M will be the additive identity or 0 element of R by M. So the 0 plus M, we can write 0 plus M is the 0 element, and 1 plus M. We have stated here it is a ring with unit element, and what is its unit element? 1 plus M is the unit element of R by M, where R modulo M, where 0 is the 0 of ring R and 1 is unit of ring R. Then 0 plus M is 0 of R by M, 1 plus M is 0 unit of R by M. This we have. Now what we want to prove is the first part. We shall assume M is maximal ideal. That is the first part of our proof. Let M be a maximal ideal. Maximal ideal of R, ring R. This we have assumed. We shall prove that R by M is a field. Now when R by M will be a field, earlier we have stated here R by M is commutative ring with unit element. We have stated here the unit element also, and because R is commutative, R by M is also commutative. So a commutative ring with unit element becomes a field. We know that if every non-zero element of it has multiplicative inverse. So therefore it is sufficient to show that every non-zero element of R by M has multiplicative inverse. So we shall only need to show this, or it is sufficient to prove that every non-zero element of R by M has multiplicative inverse. Now we shall consider an element of R by M. It is of the form R plus M. We shall consider an element A plus M, and it is not 0 means A must not belong to M. So let where A belongs to R, and then A plus M be non-zero element of R by M, and A plus M be a non-zero element of R by M. So it is non-zero means what? A plus M is not equal to 0 plus M, because we have written here 0 plus M is 0 element of R by M, and therefore A plus M is not equal to 0 plus M, and that's why A does not belong to M, or 0 plus M simply M. So A plus M is not equal to M means A does not belong to M, otherwise A plus M will be equal to M. So therefore A does not belong to M, and we have here A belongs to R but A does not belong to M, and we shall show that this A plus M has multiplicative inverse. Now we shall consider a ring, or which we shall consider an ideal generated by A. Now an ideal, or this is A, we denote this by this symbol A, an ideal generated by A, and that is AR. R belongs to R, is an ideal generated by A, ideal of R generated by A. See, this actually we have an example of this in our lecture number 8. You see that lecture where we have proved this forms an ideal of R, and it is known as generated by A because all the elements of this ideal are multiple of A. A is fixed, R varies. So AR1, AR2, etc. And for this you refer our lecture 8 example 2. And I shall see lecture 8. In the playlist of ring theory, you see this lecture 8, example 2. This is an ideal, and which is known as ideal generated by A. Now what is our assumption here? M is ideal. So again the sum of two ideals is an ideal. We have shown that result also, or that example also, in the same lecture. Then A plus M, ideal generated by A plus M, is sum of two ideals, being sum of two ideals. Is an ideal. This is an ideal of R. Now we have, see, this M is maximal ideal, and this is also an ideal, A plus M, and R is ring. So therefore the relation between these will be M is contained in A plus M is contained in R. Now M is contained in or subset of A plus M, and this is subset of R. This is ideal of R, so therefore it is subset of R. This is the relation we have. And see here, M is the proper subset of A plus M because A belongs to this A plus M, but A does not belong to M, and therefore but M is not equal to A plus M, since A does not belong to M. A does not belong to M, and therefore M is not equal to A plus M, and M is maximal. M is maximal. By definition of maximal ideal, M contained in U contained in R, either this middle ideal is equal to M or this middle ideal is equal to R. Actually there is no ideal in between maximal ideal and ring, and because these two are not equal, this must be equal to R. Then since M is maximal, maximal ideal, this is our assumption, M is maximal ideal, we must have A plus M is equal to R. So this is the result we have. This ideal must be equal to R. Now what is the meaning of this? Every element of R is of this form, A plus M, that is some multiple of A. What is this A? This A is multiple of A, and M means an element of M. So every element of R is expressed as sum of these two. Therefore every element of R is expressed as sum of multiple of A and element of M. Sum of multiple of A. Sum of a multiple of A or is sum of some multiple of A and an element of M. So this is capital M. ideal. So this is what R is expressed, and we know R is ring with unit element. So R is commutative ring with unit element. Now 1 belongs to R. So therefore this 1 is an element of R, and this 1 can be expressed as in this form, sum of two elements, which first part is multiple of A and second is an element of M. So 1 belongs to R, therefore there is an element B, B belongs to R. B belongs to R and X belongs to M, such that this 1 is written as B means we have considered multiple of A as A into B. These are considered, in, for example, B or any other letter can be considered multiple of A. It is AR. Here we have considered AB, this element, and plus M, and some element M we have denoted by X. So thus we have expressed this as 1 is equal to AB plus X, and from this what we shall get is therefore 1 minus AB, 1 minus AB, which is equal to X, and this X is belonging to M. This result we will have. And now we will consider that A plus M, what is the element is here A plus M, and or otherwise we shall add from this relation, we shall consider from 1 plus M is equal to, adding M on both sides, that is AB plus X plus M, or this gives 1 plus M is equal to, what is AB plus X plus M, X plus M, this can be grouped and we see X belongs to M, therefore X plus M is M by closure property. This is an element of M added in M, so we shall get it as M, capital M. So this is AB plus capital M, and thus 1 plus M is AB plus M. But what is AB plus M? By product of cosets in quotient ring. So we have seen earlier this is equal to AB plus M is now written as A plus M into B plus M. This product of quotient is defined as AB plus M. You refer that lecture also, and then you will get. Here also we have written the addition of sum of two ideals is an ideal. You can see the same lecture 8, and this is example 4 for these two, and this is the quotient ring. You see the lecture of quotient ring, there we have defined this product. But you see now this, so what this gives, the product of these two elements A plus M into B plus M is equal to 1 plus M. So here we should have to write there is element B belongs to R and B not equal to 0. Non-zero element we have to consider here, non-zero multiple of A, and therefore here this is also not zero element of R by M. This is non-zero element of R by M, and their product is what? 1 plus M. What is 1 plus M? 1 plus M we have written unit element of R by M. So the product of these two elements is unit element, means these two are multiplicative inverse of each other. So this shows that multiplicative inverse of A plus M is equal to B plus M, and thus every non-zero element has multiplicative inverse. We have considered a non-zero element as A plus M, and we have shown there exists another element B plus M whose product is unit element, and thus every non-zero element has multiplicative inverse and it becomes a field. R by M is a field. So therefore every non-zero element of R by M has multiplicative inverse, and it is already a ring, commutative ring with unit, and it has every non-zero element has multiplicative inverse. Therefore R by M is a field. This completes the first part. Assuming M is maximal ideal, we have proved R by M is field. Now the converse part, second part, we will assume R by M is a field, and then we shall prove M is maximal ideal. Second part, conversely, suppose M is an ideal of R and R by M is a field. We shall prove that, this is assumed, we shall prove that the converse part, this if and only if means implies and implied by. This implies M is maximal ideal. We shall prove M is a maximal ideal. And to prove M is maximal ideal, by definition of maximal ideal, we shall consider it. And first we have M is not equal to R. Let M not equal to R, and there is an ideal, another ideal we shall have to consider, ideal U, such that M is subset of U is subset of R, and M is not equal to R. Then when this M will be maximal ideal, either M is equal to U or U is equal to R. And if M is not equal to U, then we have to prove U is equal to R. Now if M is not equal to U, we shall prove that then M will be maximal ideal if U is equal to R. So this we shall prove. We shall assume M is not equal to U, then we must have U is equal to R. That means there is no ideal between M and R, and therefore M becomes maximal ideal. Now we have M is not equal to U. So therefore an element in X, there exists an element X in U which is not in M, because M is contained in U. Since M is not equal to U, M is proper subset of U, and therefore there is at least one element in U which is not in M. So therefore let X belongs to U such that X does not belong to M, and therefore what we will have is X plus M X is not in M. Therefore X plus M, this is an element of R by M, and X is not in M, therefore it is not non-zero element. X plus M is non-zero element. If it is X plus M is equal to M, then it will be zero element. Is, or you may write X plus M is not equal to 0 plus M, and therefore X plus M is a non-zero element. Non-zero element of R by M. Now further we shall consider another element which is non-zero element of R by M, and for that purpose we shall consider here Earlier we have used x letter, so we may use instead of x we may use y, so that there will not be overlapping of the notation. It may be different, that, and therefore we shall consider y belongs to u such that y does not belong to m, and then y plus m is not equal to m, and then y plus m is a non-zero element of R by M. Now what further we shall assume as, let Z belongs to R and Z does not belong to M, then Z plus M is a non-zero element. Similar to this, non-zero element of R by M. This is also a non-zero element of R by M. Every element of R by M is of this form, and thus we have taken two elements of R by M. So this y plus m is an element of R by M. Y belongs to u, y does not belong to m. Z plus m is an element of R by M, and because R by M is filled, that is our assumption, it is closed under multiplication, and these are two non-zero elements, their product is also a non-zero element, and therefore there exists, we shall consider the product. For product there exists alpha belongs to R. So there exists, since R by M is a field, see, there exists alpha belongs to R such that the product of these two, y plus m and z plus m, these are the two elements of R by M, and by closure property this is equal to an element of R by M. Product of two element of R by M is an element of R by M, and it must be also this form of this form, R plus M, and for that R we have considered here alpha here. So this is alpha plus M. Now by product of these cosets, what we have is yz plus m is equal to alpha plus m. And again this implies yz minus alpha belongs to m, because see, a plus u is equal to b plus u. This implies a minus b belongs to u. The elements two cosets are equal, then their difference belongs to the set u, and thus here we have yz plus m is equal to alpha plus m, therefore their difference yz minus alpha belongs to m. And but what is our assumption here? M is subset of u. M is not equal to u, but m is proper subset of u, or m is not equal to u, m properly contained. So then here here we have written m is not equal to u and m is subset of u. So this is in m means it is in u. So therefore yz minus alpha belongs to u, since m is subset of u. Now what is u? U is an ideal. There is an ideal u. So therefore this is an element in the ideal. And again what we have is earlier element, see, yz. Y is an element of u and z is an element of R. So further also, or we can write also y belongs to u, z belongs to R. This we have here, and by since u is ideal, their product belongs to u. This implies yz belongs to u, since u is an ideal of R. This is the second property of ideal. The product of an element in R and element in U is in U. So this is yz is in U. This is element in U, this is also element in U, and because U is subgroup under addition, their addition difference is also in U, and here we shall consider their difference, and thus therefore we have yz minus alpha, the difference of these two, yz and yz minus alpha. This also belongs to U, since U is subgroup under addition. And therefore their addition or difference is also in U. But what is this difference? Yz minus yz, and minus of minus is plus alpha, so it is only alpha. Alpha belongs to U. So now you see what we have here is alpha belongs to R, and what we have obtained here is alpha belongs to U. That means every element of R is an element of U, and thus alpha belongs to R. You see this, and we have obtained this. Alpha belongs to R implies, from this alpha belongs to R, we have obtained alpha belongs to U, and therefore this R is subset of U. A ring is subset of U. But what is U? U is an ideal of R, and an ideal is always subset of R. But U is subset of R. U is ideal of R, and therefore U is subset of R. And thus what we have is these two must be equal, and hence U is equal to R, and this is what we wanted to prove. So what we have started with that M is an ideal. M is an ideal which is contained in A plus M, and that is contained that is U we have considered here. M is an ideal. M is contained in U is contained in R. And if M is not equal to U, then U must be equal to R, and we have proved this. U is equal to R, and M is not equal to U, then this implies U is equal to R. So therefore this proves M is maximal ideal. M is a maximal ideal of R. So thus we have proved the second part also, or the converse part also. Assuming R by M is filled, we have proved M is maximal ideal. So this is an important theorem which states necessary and sufficient condition for M to be maximal ideal in terms of its quotient ring. I hope you will understand the proof. The remaining part we will continue in our next lecture. Thank you for watching the lecture.